All right. So everybody, I'm Dominic. I wasn't really able to prep for this a lot. So there's going to be like a lot of content here. If I say anything that is inaccurate, or if you have a questioning point, or if you think that something that I say maybe doesn't reflect what is actually happening, you feel free to stop me, interject me. There's kind of a lot of things to be covered here. Windows doesn't do a really great job at covering a lot of things that I'm going to be talking about. So please feel free to interject and stop me. So I was on co-op last semester, so a lot of you may not have been introduced to me yet. My name is Dominic. I'm a third year currently. Currently, I'm co-oping at Draper Laboratory as an offensive cybersecurity researcher, doing a bunch of evil, hacky things. Over last summer, I was a security engineering intern at Susquehanna International Group, a major financial tech company. And I've also been a speaker and instructor at Black Hat USA, Black Hat Europe, DEF CON, Hack Space Con, Hack Miami, soon to be B-Sides Rock, I'm sure more. So just kind of get into an agenda. When kind of being asked to do an advanced talk, it can be a little hard to figure out what exactly I'm going to cover, what I'm going to talk about. There's kind of a lot of topics under an umbrella to talk about. So kind of going into this presentation, what I want to talk about is kind of walking you through the process of when you log into Windows, what happens, how are you authenticated, how are processes created, the entire process up from authentication when you are prompted with a login prompt all the way to when you're interacting with the desktop. So authentication is kind of any process of creating, submitting, and verifying credentials. I'm sure all of you are familiar with this. When you're prompted by Windows to kind of log in, this is kind of what happens on the back end. So a lot of people maybe think that authentication is handled by LSA, or the local security authority, when in fact this is kind of just an authentication model, or kind of a base that a lot of other things can be based off of. And so the LSA is kind of comprised of a lot of different authentication packages that can then be used to authenticate. So these authentication packages are verified by what are called authenticators. So these authenticators may be, NT hashes, LM hashes, all these different hashes that can, prove that you are who you're saying that you are. And then obviously, once we're kind of authenticated to a server or to a workstation, we don't want to continually prove that we are who we say we are whenever we, want a new process or whatever it may be. And so that's when kind of LSAS and a few other processes kind of come into play. So LSAS is the Local Security Authority Subsystem Service. And so this is a process that is running on every Windows workstation and server. That is going to go ahead and store your credentials or your tokens. And then they'll also be stored in the Security Access Accounts Manager database. So NTLM is one of the kind of main authentication packages, as I was saying, that is under LSA, Local Security Authority. So NTLM is the new technology land manager. And really this authentication package is just a suite of security protocols that are going to be used for authentication. So NTLM is primarily a challenge response based authentication. In the next slide, we'll kind of get into what that challenge response actually looks like. This is primarily going to be used for local authentication. So think, logging into like a Windows 10 machine, not like a domain controller or like a Windows server, but just logging into like a Windows 10 machine, what really happens when you set your password. It's also kind of possible for this to be extended into the Active Directory domain space or to a domain controller through NetNTLM, which will take the NTLM hash and then send it over the network. So kind of how this process works, there's kind of an initial negotiation that happens. There's about 6 steps here. That is how the challenge response works. So first, if you can see here, whenever this negotiation message is sent, Really, what that is it's any kind of domain information. What is the domain name, what is the time, things like that, as well as a username. Once that information is sent, a 16-byte random number challenge will be sent to the client. So whoever just sent that negotiation message. Once that's received, only then will the password actually be hashed and then sent to the server. Once it has both the username and the password, the server will compare it against its SAM database, so that's Security Accounts Manager, and then it will encrypt the challenge with the hash. If it is able to compare the challenge and the hash with the SAM database, then it will kind of validate your login and then permit you to access the system. Kind of the problem with NCLM right now, though, is that it is pretty old. NCLM was released in 1993. And at this point, I believe that Microsoft is considering it not deprecated, but it is highly suggested not for use since 2010. The thing about NCLM, though, is that it is still kind of used for local authentication. The big problem with NCLM is when it comes to the kind of network or Active Directory kind of authentication requests. So the problem with these requests is that because NCLM is considered broken, if somebody decides that they want to kind of man in the middle these requests, they're able to get your hash and then do anything with that, like pass the hash, etc. So now to kind of replace NCLM, we now have Kerberos. And Kerberos is what's primarily used for domain authentication, to your Active Directory servers. So say you have a Windows 10 workstation. This is what is sent from the Windows 10 workstation to the domain controller. So although Kerberos has replaced NCLM is still used for local authentication because it's not prone to the man-in-the-middle attacks. Let's see. So Kerberos is kind of a lengthy topic, and I could have an entire talk just on Kerberos. I'm going to kind of try to give you guys at least a little bit of a high-level overview of it. So the entire premise of Kerberos kind of comes down to tickets. And so these tickets are going to be, delegated by what's called the KDC, or the Key Distribution Center. And so, whenever you go ahead and request a password or request authentication to a domain controller, instead of doing the challenge response like NCLM, instead what you're requesting is a ticket ticket as well as a session key from the KDC. What the KDC is just the KRBTGT, which is just basically a user on the domain controller. So the KDC is also composed of both the authentication service and the ticket granting service, which are both just normal services on Windows. You can basically think of it as that. And so this is kind of like, imagine this as the first 3 steps of kind of NCLM, where you're doing this challenge response. You're trying to get a ticket to then be able to negotiate with Windows. We're going to get into a diagram in a second that will kind of let us into a lot more here. Also, like we mentioned with LSA being these authentication models, we mentioned that we have NTLM, NT hashes, LM hashes as the authenticator for the authentication model. Here, instead, the authenticator for Kerberos is going to be a privileged attribute certificate, and that's kind of going to be what you get at the very end. So let's kind of go here to a diagram. Again, this is going to kind of be a lot of information at once, and it can kind of be a little hard to explain, so I'm going to try my best here. But kind of at this first step here, this is going to be called the as-rec. So kind of how Kerberos is split up is you have roughly 3 processes, each with a request, each with a response. So these first 2 kind of requests here, that is a request and a response to the authentication service. The next 2 steps here, you see 3 and 4. Those are going to be requests and responses to the ticket granting service. And then the last 2 are going to be the request and response to the actual service that you're requesting. So basically, kind of how Kerberos works here is that the first 4 steps, you're really just trying to get a ticket to allow you to authenticate doing that service. So you're authenticating yourself with the domain controller, and then you're authenticating yourself with the service. So to kind of obtain the TGT, like we were talking about, the first kind of 3 steps of NZLM, or the first 2 steps here, what you're going to do is encrypt a timestamped NT hash, and then send it to the domain controller, and the domain controller is going to compare it. If you've ever done like RITSEC or ICS or competitions, maybe you've seen that your Kerberos or your LDAP authentication maybe has problems because of Kerberos or time. And that's mainly because whenever you're doing this authentication, this negotiation, it's time saving these hashes. So if there's any, if your domain controller and your workstation are out of sync of each other, obviously these timestamps are going to kind of be out of sync. Are there any questions about this? It's kind of a hard process to explain. There's kind of a lot here. Cool. So we're going to kind of shift gears here for a second. I know that I said that I was going to try to explain it from the top down, from authentication to a process. Here we're going to kind of shift gears into the processes. So at this point, we're kind of assuming, we're authenticated in Windows. What happens now? What kind of processes are happening? What do processes even look like? What are processes? And then we're kind of bring it back to authentication towards the end. So here is kind of what the Windows OS architecture looks like. It's split up between the kernel mode, or the predictor mode, and the user mode. So the kernel mode, you can think of that as the hardware. There's unrestricted access there. There's direct CPU instructions, and there are really crashes to be expected here because you're giving direct CPU instructions. And this is kind of where the blue screen of death occurs directly by sending kernel mode instructions. Quite a few years ago, Windows kind of shifted gears from kernel drivers and direct CPU instructions to mostly the user mode and Windows API. So this is going to have kind of limited resources, and you kind of have to go through quite a few calls or functions to get to hardware. And here we're going to have processes and threads, which is kind of what we're going to get into here now. So we're mostly going to focus on the user mode here. Like I said, although we're in this kind of user land context, there's quite a few things here that we can do. And so we kind of go, so if you look at this from kind of the bottom up, like these DLLs, these Windows services, these are mostly like user mode things. DLLs, are just libraries that are kind of, or small pieces of code that are kind of interoperable between programs. Windows services, being almost identical to kind of Linux services as well. These are both things that kind of run in user mode, and then Windows APIs and system calls are kind of where we start kind of shifting things to this kernel land, to this kind of kernel mode. So Windows APIs kind of allow you to interact with different parts of the Windows subsystem, and a lot of these calls kind of branch off of each other. So maybe a Windows API call will call another Windows API, and then that Windows API will call a NT API or a system call, and you can end up with like 10 branches down of just these system calls until you eventually end up at a kernel routine or some running hardware. So this is kind of what that looks like. Again, we kind of have the kernel mode and the user mode. The switching point between kernel and user mode happens between the Win API and the system calls. Like I said, a lot of the Win APIs call system calls. They just do it in a safe way that prevents these crashes and unexpected things happening on the kernel. So again, we're kind of mostly focused on these kind of 3 processes here that are within the user mode. Being Windows APIs, Windows services, DLLs. And so kind of to interact with these, these components, some kind of executable file or application, is probably necessary. And so, there needs to be some kind of standard or format that, these kind of executable files can kind of take. And so that is what the portable executable file format is. Really any file that you have is going to have some kind of format, whether it be, a PDF format, Excel format, things like that. This is just another one of those. If you ever see like a .exe, this is the format this is taking. So there's going to be kind of two categories here. We're going to kind of get into those a little more as we go through. There will be both headers, which kind of contain information about the portable executable itself, and then there will also be sections which contain most of the data surrounding the executable. So we kind of see what these are split into. We see the header. There's a DOS header, a P header. All these we'll kind of get into a little more in the next few slides. But also one interesting thing we see here is a section table. So one thing that P files use a lot are offsets and pointers. And so what the section table is going to have is a lot of pointers to different parts of the sections. And so you'll see here we have like imports and data, and we'll also have your dot. If you've ever taken like 201, about like the .txt section, the .data section, things like that. That is all controlled through this P file and through the pointers in the section table. So here we just have kind of some of the headers for the P format. So a lot of the headers are kind of made up of other headers, which is a little hard to understand. But at the end of the day, kind of the P file format is just having a lot of pointers and offsets to other things so that you can always find the information that you need, starting from one point and ending up at another. And we'll kind of get into that in a second. So just kind of some of the really key headers to kind of understand are the dot stub. We'll get into this in a second, but the dot stub is kind of where all of the calculations for a P file start. And the dot stub might kind of seem trivial at first or kind of not necessary, as it is a little bit of a legacy component. But this is, if you've ever tried to execute a file, it says this program cannot be run in DOS mode. That's really all this is. That's what the dot stub is. There's also going to be a P file header, which is going to contain a lot of the metadata about the kind of file format itself. And then there will also be an optional header, which is going to provide similar information, but this is really going to provide information to the application like the Windows.h file, which really allows you to have all of the Windows calls, functions, and things like that, which are especially important. So I kind of gave you guys a lot of kind of words, a lot of explanations of what a P file is at a high level, but I didn't really explain to you, what is a P file. So this was kind of hard for me to understand for quite a while. When I first kind of heard about P files, I kind of understood them. I was able to open up PA Explorer, kind of look around, but it never really made sense to me. What it was, how this format is applied to EXEs. How the subsystem understands this format, and that really changed when I was in a class, and the entire goal was to take this executable file, or I think it was actually a DLL. And convert it all the way down to just hex, and kind of be able to take these bytes directly and manipulate them. And so there's a tool on Dominic called XSD, which is able to convert a DLL to a hex dump. Once you kind of have this hex dump, you're able to perform math on these executables. And so this is kind of what a P file format looks like in all of these values. There's going to be a few kind of specific things here that we'll touch on in a second. But the entire thing to kind of understand about this, I mentioned a second ago that the dot stub was, pretty key in doing all these calculations. So there's something called the E_LFA new. And this is where kind of all the calculations for a P file are going to start from. So this kind of value right here, or this offset, is always going to be the same. It's always going to be, start from OX3C. And what this is going to allow you to do is, all these, that to get to this header, it's going to be 4 bytes. And then maybe that header has a pointer to another header. So let's say I don't know this for sure because I haven't looked at the exact P file formats for a while. But let's say from E underscore LFA new that it's 4 bytes to the P file header. It's another 4 bytes to the offset or to the optional header. At that point, I could say, let's take OX3C, let's add 4 bytes, and I have a pointer to the P file header. Once I have a pointer to the P file header, I know all of those bytes. Let's say I add another 4 bytes to that pointer or that offset, and I have maybe another pointer to something else, maybe to an import table, or maybe to some more information I need, or maybe an entry point, right? And so all these things are pretty easily calculated, and that is kind of interesting. That really kind of changed things for me when it came to P files. So we're going to kind of shift gears here again to kind of manage code. Looking at kind of P files, we're really working in executables in general. We're kind of looking in this unmanaged space in general with P files. So you think C, C++, really anything that doesn't require some kind of virtual machine or something kind of intermediate to kind of compile with. So managed code is kind of a solution to this. If you ever took 124, another Java class, Java uses its Java virtual machine for all of this. And so Windows kind of has, or Microsoft has its own implementation of this called .NET. And so this is kind of a framework that doesn't necessarily replace C or C++ currently, but it's just kind of another means of getting or interacting with a system. So it's going to use what's called the Common Language Runtime. Think of this just like the Java virtual machine. That's going to be used for compilation rather than compiling directly to machine code, like you would see, GCC and things like that. So .NET code, whenever you compile it, if you're in Visual Studio and you say build this project, instead of being built into machine code, it's going to be built into what's called the Common Intermediary Language, or the CIL, which is then going to be built into another standard intermediary language called the Microsoft Intermediate Language file. And so all this is considered managed code. But what this kind of allows you to do is access a lot of these kind of Windows kind of subsystem parts through the Common Language Runtime, because that has a lot of the kind of processes and things that you kind of need. So whenever whenever you start an executable, or whenever you start something that's built with .NET, it's going to start what's called the just-in-time compiler that's part of the Common Language Runtime. And so compared to the kind of Java virtual machine, this is going to, right when you start the executable, as it is running, it's going to be compiling this from the intermediary language to the machine code. And this really allows you to have consistent compilation methods across multiple languages. So .NET isn't necessarily a language. C# is a language, J# is a language, F#, Visual Basic, and Boolean are all languages that use .NET. PowerShell also has .NET features. So all these languages can kind of be universally used across each other. And then this also allows us, just like Java, to kind of use it across multiple platforms as well. So here, you kind of see how it's transformed from, the .NET runtime into the intermediate languages, and then eventually the native code. And here's just kind of a diagram of how this happens as well. So there's a few kind of things. The interesting thing about the CLR, because it's kind of controlled by Microsoft, is that it allows it to, instrument a lot of security features directly when an executable is running, or when a program is running. And so two of these things that are instrumented within the CLR itself are the event tracing for Windows and the anti-malware scan interface. So event tracing for Windows is a kind of logging and tracing manager that is, kind of used by user applications and kernel drivers. And so this is going to do all of the logging for your application directly from the CLR. And then, if you've ever opened things like event viewer or logs, things like that, this is kind of directly logged to those sources. And that again could be an entire talk of itself of how the ECW works and how subscribers and things like that work and providers. One other thing which is instrumented by Defender, this is separate from Defender but is used by Defender for its kind of collection, is going to be the anti-malware scan interface. And so what this is going to do is during runtime, it is going to scan the program for malware. It's going to look for it's going to look for strings. It's going to look for files and memory, and you can even do things like content source, URL, IP reputation checks, and things like that. So this is going to be a lot more. This is going to be your dynamic signatures versus your kind of static signatures that normal Defender kind of supports. But the entire point of AMSI was kind of to be vendor agnostic. So whether that's Defender or another antivirus, they're all kind of able to hook into AMSI. They will all get the same data. So whether it be through a portal executable and through unmanaged code, or whether it be through managed code, eventually we get to some kind of process. And so a process is just going to maintain and execute some kind of application. And so this is what the application is going to look like after execution. And so there's quite a few different components of processes. Some of these may be familiar to you, some of these may not. There's going to be some kind of virtual address space. So if you're not familiar, rather than having physical memory, applications are all given virtual memory. So when you were in CSEC 201, if you've taken that class yet, rather than adding bytes and manipulating physical memory, instead you are really just manipulating some kind of virtual address space that is handled by the Windows itself. You also have whatever code you executed, and then you also have handles, and so handles are kind of used to track and use all these different processes. There's also going to be some kind of security context to your process. So we'll get into that a little later with tokens and how kind of Windows login and authentication kind of interacts with processes. But the security context is really just going to be what privileges does that process have. It's also going to have things like a UAD, variables, and a few other interesting things here as well. So in memory, what a process really looks like is just like this. This diagram, it might be familiar to you, or some of these different things that I cover. But we have our code or our sections. We have over variables, and then we obviously have a heap. Stack versus heap, just like you've all learned in CSEC 201. This is just a diagram as a process rather than as some weird memory address, right? One thing that might not be, as familiar to you guys is the environment block. So the process environments are kind of this way for storing a lot of this data, or a lot of the information surrounding a running process. So rather than the process memory itself, which you generally think of, when you think of a stack and a heap and, the code running the application, we also have this entire other part of it called the PEB, the process environment block, which contains the information. There's also going to be things like the E process, which are going to define the structure of the process, as well as the kernel process, which kind of, defines all of this structure kind of surrounding the process, how it's executed, things like that. The PEB also is going to define things like the loader or the LDR, which is going to be how a lot of these DLLs are loaded into your application. So like I mentioned earlier, DLLs are kind of this way of, taking small portions of code and kind of moving it throughout different applications. And so, the LDR is going to kind of handle that. Think of, if you've ever heard of like kernel 32.dll, things like that. And the LDR is kind of going to be what allows you to kind of load this. And PEB is really just a structure in memory that you can use. So parts of a process, also we also have threads. That was after the process environment block. Now we have all the threads of an application or of a process. And so a thread is just an executed unit employed by a process that could be, scheduled based on device factors. So if you remember apply through Java, you might have started messing with some threading, and you know that you can't really directly impact when a thread is scheduled. The kind of CPU scheduler kind of defines, based on CPU memory specifications, what your priority is, things like that, when your thread is going to be scheduled to execute. So just like just like processes have different information and different kind of memory structure, components will have the exact same thing. So threads have a stack. Threads will have thread local storage or TLS, and they'll also have some kind of context structure. So here is kind of what a thread looks like. So there is generally kind of a thought or some kind of phrase that every process for a user is a thread for a kernel. I don't really know exactly where I first heard this, but that's just kind of an easy way to kind of think about it. And because the virtual address space for a process is all the same, every single thread, unlike a process, is going to share the same memory space. So every single process is going to get its own virtual address space. Every thread is going to share the same block. Just like there is an environment block for the PEB, there will also be an environment block for the thread. So just like it holds the information for a process, the TEB is going to hold the information for a currently running thread. The thread environment block is a part of the thread information block. So this is kind of one of the parts where I told you, this information is kind of hard to find for Microsoft itself. If you look up right now, thread information block, I'm not sure that you're going to find anything on Google. It certainly won't be the first result. Thread environment blocks, you can find quite a bit of information about, but TIB specifically, you cannot. And this is just kind of one of those things where, the kind of information that you might find or resources you might find may kind of vary. But from my understanding, the thread information block, the thread environment block is a part of the thread information block. And that's just going to, contain more information about the specific thread. Kenny.
How do I find out more about this?
I honestly have no idea. I think that I found like one blog post about it. The problem with Windows is that a lot of this information is kind of safeguarded. I think I found out about TIBs through a class that was not cheap, and that I didn't pay for. And so, maybe you'll be able to find some information, but that's why we have things like this to kind of spread the word as well. So, yeah. So I don't remember how I found it. I know it's a thing. If you try and debug it, I don't think you'll really find it. Maybe, with process environment blocks, thread environment blocks, things like that. A lot of these you can go into WinDebug, attach to a process, and be able to dump all of these. When it maybe if you want to kind of investigate this more, that's an avenue that you can do. Kind of attach to a process and kind of digging into the tab a little bit more. But kind of looking into the security of these processes, when you were taking CSEC 201, you did a basic stack, buffer overflow, whatever, but you might have also found out about ASLR, which kind of mitigates a lot of these basic, stack buffer overflow attacks, because instead of having some kind of consistent, address space, instead of going to randomize all the addresses in a process and DLL as they're loaded in memory. And so, whenever you maybe execute an executable, you maybe notice that all the addresses change every time. And that's kind of a result of ASLR. And so this kind of caused a big issue for Windows, in which all these Windows API calls rely a lot on these memory address spaces. And so as a mitigation of this, they built the Windows loader, or Windows FH, as I was saying, was instrumented through the optional header. And so this is going to handle finding all those addresses for you for your Win API calls, your function calls, things like that. We also have DEP, the Data Execution Prevention, which is going to mark a page of memory as non-executable, and rather than mitigating these buffer overflows, it's going to mitigate these buffer overruns. So kind of just talking about security a little more, those were direct mitigations against attacks to a process or to memory. We can also look at specific things and how processes and authentication interact. So tokens are going to be used to describe the security context of a process or thread. If you remember, I told you that within memory or within part of a process or thread, there is a security context. So the security context is going to be controlled by these tokens. So just as maybe there is a web token, a JSON token, or any kind of cookie, you can think of this just as the same. This is going to be some kind of way for you to prove that you are who you say you are without re-authenticating. So this is going to be kind of used so that a process or a thread can have the same permissions and privileges as you without re-authenticating with your hash. So a process will obtain a default access token from its parent process. When I say parent process, if you are starting executable from the command prompt, cmd.exe would be the parent process, and then if you start that cmd.exe from Explorer or whatever it may be, that would be its parent process. You can kind of keep going down the line. And then a thread will always use the access token on its process, unless when you code whatever the process is or whatever the application is, specifically say I don't want to use this token. So tokens are kernel objects that, like I said, represent privileges and memberships. And you can use really any authenticator. So if you remember, like I said, with LSA, they always have, as part of your authentication package, an authenticator. So the authenticator could be your passwords, your XML hashes, your privilege attribute certificate with Kerberos, or it can also be from impersonation, which we'll talk about in a second. So here, we have a kind of diagram of how this authentication works. So kind of here we see that after authentication, authentication is handled by LSA, which I again mentioned is an authentication model. Once you are authenticated, once you get through that command prompt and you're presented with a desktop environment, you will have an interactive login session, which will, kind of be your, desktop environment, things like that, whatever your interactive session is. And then you'll also have an access token that is created after that. And that access token is what is used to authenticate, Chrome, things like that, all of your processes. And this all happens, kind of within what is called Windows Station 0. So here, there are different types of access tokens as well. So, one of the first ones, when you're logging into Windows Station 0, the primary access token is what is created, as well as your interactive login session. So this, used by processes is going to be used to define your user contacts, your permissions, etc. And then you'll also have a restricted access token, which is going to be used for a majority of your processes. So think, Chrome, command prompt. And so this, rather than having, you don't want Chrome to have access to all of your permissions or all of your privileges. So instead, you're just going to give them small pieces of your privileges and permissions, that can be created during your process creation, or, these tokens can also be created using the Windows API. So, rather than always create these tokens, we can also impersonate a token. And so this is kind of going to be how multi-client kind of applications work. So if you think about SMB, right? SMB is kind of one application that multiple clients can connect to. And how these clients kind of determine their privileges or these access or their access is kind of through token impersonation. And so for an impersonating thread, there'll be one or two access tokens created for each that are going to describe the context of the impersonating client. Yeah. So here we kind of see, how these tokens are used. Here we see, on the left, you see that we're logging into Windows Station 0 using the password. We have a primary access token used for specifically Windows applications. So Explorer.exe, Command.exe, these are all Windows default applications that are going to use the primary access token. I'm going to have, these are guaranteed by Microsoft that they're going to be safe and have the correct permissions, etc. So they're going to use the primary access token, and then whenever you create a new token for some kind of third-party external process like Chrome or Spotify or things like that, those will all use restricted tokens. So, for example, this token has the access requirement of reading only, and then it'll be able to compare its access to the access of whatever file it wants. So say you're trying to open your downloads, or open your files, or upload something to a web server. Like say you have a web application open in Chrome, you want to upload something. If you have access to that file, it will be compared to whatever your restricted access token is, if you have access to that file. And so here, we see that the restricted access token and the primary access token are all derived from this original primary access token of Explorer.exe. And so this command.exe and government.exe are all child processes of Explorer.exe. So you can't get any more permission than its original primary access token from Explorer.exe has. There are also, special token privileges that tokens can have. So, here is just a list of kind of privileges that Lamb can have. So, like maybe it can shut down a system, So if Chrome has, if the restricted access token for Chrome has SE shutdown privilege, it's possible that, Chrome can now have the permission to shut down the system. One of the most notable kind of permissions here is the SE impersonate privilege. And so, like I said, with impersonation tokens, the SE impersonate privilege is going to allow you to impersonate any client after they've authenticated, even if they are an underprivileged user. So, say you are just a local user, whatever, you don't have any kind of permissions, but you specifically have this SE impersonate privilege as your primary token. This, has to be set, prior by an administrator to your specific user account. After you have this specific privilege to your token, if an administrator account, a local administrator account, were to log in, at that point, because that local administrator account is logged in and has a token on the system, at this point you can impersonate their token as yourself, and you can open a new command prompt. And instead of having these local user rights, you would now have the rights of this local administrator. So that's a pretty important and a pretty powerful privilege to have. So now that we've kind of covered how processes authenticate, how processes are created, things like that, we can kind of go over how processes communicate. So like I said, SMB is going to have this client server model. And so if you have a client and server that want to communicate over two different devices, but let's say not use traditional network protocols like HTTP or TCP, things like that. Instead, they can use inter-process communication. And there's kind of two methods of this. One being shared memory. So like I said, they all have virtual address spaces. Let's say I have thread A that wants to communicate to thread B, or I have process A that wants to communicate to process B. If they have the same address space, i.e. not a virtual address space, or not two different virtual address spaces, they can both, one sets one memory address and the other returning memory address. Obviously that has a lot of issues with kind of syncing and deadlocking and things like that. Or you can also do, message passing. Um, so kind of one form of this inter-process communication is called Windows pipes. So what a pipe is just a shared section of memory that allows processes to communicate, and Windows pipes kind of facilitates all of this communication. And you'll note because it is a shared section of memory and it's not actually a protocol, there's no kind of network communication happening here. There are kind of no protocols because it's just a shared section of memory. And so you can write a pipe client and a pipe server to communicate to each other. And then there are also two different types of pipes. There will be a name pipe, which is one-way or duplex communication, and is used to communicate between different machines. So say I have a Linux machine and a Windows machine. If my Linux machine, has one process and my Windows machine has another, if I have a named pipe, I'm able to communicate between the processes with no protocols, just these shared sections of memory. Unnamed pipes are anonymous and one-way communication. The thing to note about this one, though, there will, it's only local. You can't communicate over a network with these pipes. Yeah. So, kind of throughout this entire presentation, we covered a lot of the kind of user land portion of Windows internals because this is, easily applied to Windows development and using the Windows API and functions, things like that. But, there is an entire another world out there of kind of the Windows kernel space. In the bottom here, there's things like the kernel layers and the IO layers. All of which are kind of equally as complex as kind of what I covered here, or even more. So I definitely kind of encourage you to kind of do your own kind of research here and kind of dig deeper if that's something that interests you. That's it. Any questions? All right. Thank you.